Now let's have a brief introduction about microcontroller peripherals and how they can be programmed. So peripherals are base unit within the microcontroller to achieve a specific purpose. For example, a timer peripheral is used to provide alarms, counters, or cyclic call to a function. Similarly, I2C can SPI can communicate with external sensor or provide data to and from microcontroller. Other peripherals may be provided to do some calculations such as CRC peripheral for CRC calculation or SHA peripherals to do some SHA-128-256 calculations and others as we discussed, for example Wi-Fi and others. So peripheral registers provide means to configure and track the status of the peripheral during processing of a job. For example, when you could program a timer peripheral to cyclically execute a function, it might have a register in which you feed a number which signifies how many seconds after you need to call a function, and then another register which might take an address of a function. Then the first register keeps, and then there is another register which keeps decreasing, and when it becomes 0 it calls the function and then reloads itself from the value you provided in register 1 for cyclic timing. So for example, another example is you have a UART bus which need to run at a certain baud rate to communicate with the external device. In order to set up the UART peripheral to run on a fixed baud rate, you might need to program the peripheral registers with certain values so that it can communicate properly with the external device. And these details can be seen, or basically how to program a peripheral can be seen in the datasheet provided by the silicon vendor. So this slides this slide basically presents two peripheral registers from a UART on STM32 103 RB board. So each register within the peripheral has a fixed address space available in the memory. So for example, for USART1, the address space is from hex 40013800 to hex 400113BFF. So all the registers of peripheral USART1 need to be within this address space. So the address 0x40013800 is the base address of USART1 peripheral. Then we have picked up two registers randomly from this peripheral. So the first register is USART SR1 and it has an offset, address offset, which is basically the address offset from the base address. Since the address offset is 0 from the base address, so the address of register SR is 0x40013800. Then it has many bit fields. So for example, bit field PE, which is read only and starts from bit 0 in the register and it's just 1 bit wide. Then second is FE, which is starting at bit 1 and again it's read only and 1 bit wide. Similarly, you can see any ORE idle. RxNE is ours not read only, it can be read and write. So what this means is it can be read and cleared with by writing 0. So RxNE is also 1 bit wide, starts at offset 5. Then this, if you see the reserve section in this, the reserve section starts from 10 bit offset number 10 to 30 and spans up to 31, so it's somewhere around 22 bits long. So in this 32-bit registers, only first 10 bits are usable and rest 22 bits are reserved. Similarly, you can see there are multiple bit fields within USART CR1 registers, and its offset is 0x0C, which means that its absolute address will be 0x400138C0C. So basically, the address of a peripheral register can be calculated by adding the offset to the base address, which is clear. Okay, so now the bit field within the peripheral has certain uh, attributes which we can see. So the first attribute is the offset, second attribute is the name, and third attribute is what is the access type of that bit field. So access type could be read write or read only or write only or reserved. So, so as we discussed before, that C is the most prominent language in embedded system programming currently. So typically in C, a register is represented using macros as shown in this slide. So SR register is represented by adding the base address to the offset, and CR1 register is represented by adding the base address to its offset, and it is converted into a Uint32 pointer, and then any operations are done on this pointer. Now, in order to set certain given bit fields within this a given register, macros set bit range and get bit range are implemented, which use the register, which is the USART SR hash define, then the offset, which you can see from the previous slide in the diagram. The offset for P bit field is 0, then you have count, which is the width of the bit field. So for P it's just 1 bit, and then the value you need to write at that bit range. Similarly, get bit range returns you the value currently set at that bit range. So these are the macros. So this is how we try to program in C a certain register's bit fields. So let's try to achieve that in C++. So simple program to program a bit field within a given register in C++ can be implemented using a class and providing two methods, set bit range and get bit range, which take 3 inputs for get bit range and 4 input arguments for set bit range. So what are those arguments? So for get bit range, you need to know the address of the peripheral register. Then you need to know the offset of the bit field, and you need to know how wide that bit field is. For set bit range, where we want to set a value within that bit field, we need to know the peripheral register address, then the offset of the bit field within that register, and then the width of the bit field, and then what value we want to set in that bit field. So this is a very simple class implementation for a bit field. But what we'll do now is we'll go through different C++ features and try to apply those features one by one to this class so that we can improve this class to achieve a more efficient version of this bit field and try to represent register by collecting those bit fields, and then by collecting those register try to represent a peripheral, and then by collecting those peripherals try to represent a microcontroller, which is our final aim.